Section 3.3 is titled Logarithmic Functions and Their Graphs. We're going to look a little bit at graphs of logarithmic functions, but really only to kind of build a basic idea of what they are. This section really kind of introduces us to the mathematics that we need to solve a lot of the exponential modeling type problems that we have been doing in the previous two sections, where we've been using the graphing calculators to help solve them because we've lacked the mathematical background needed to solve the problems. Well, in this section and the next couple that follow, we kind of start to develop that the mathematics that's required to solve those problems. And the mathematics that's required is a basic understanding of logarithms and logarithmic functions. I want to begin by looking at a graph. It's actually the only graph that we're going to look at in this particular lesson. And what I'm choosing to look at is a graph of exponential and logarithmic functions. Now first let's talk about the one that is recognizable to us. If we look at this one that's written down in blue, this could be described as y equals a times b raised to the x. That's how we described it in section 3.1, or more simply, if a was just 1, let's just make it as simple as possible. If a was simply 1, this would be y equals b raised to the x. Okay, so that's the function in blue. Now if we go back to an earlier lesson, and I'm struggling which lesson it was, I think it's lesson 1.5, quite possibly. Section 1.5 is where we talked about inverse functions. And we've said that inverse functions have a unique visual property, a property amongst their graphs, in that they are reflections about the line y equals x. And so what I've done is I've taken this exponential curve, y equals b raised to the x, and I've reflected it over this line. And when I reflect it over this line, we get this graph. Okay? And that particular graph has an equation also. The equation of this graph is x equals b raised to the y. As we know that when we find and define inverse functions, we do it by just taking the x and the y variables and we interchange them. We just flip them. So if I do that to this y equals b raised to the x, we get x equals b raised to the y. Now we typically want functions written y as a function of x, not x as a function of y. So we take this and we rewrite it. And when we write it with a logarithm. This is rewritten y equals log base b of x. It's important to remember that when we are evaluating these logarithms, and I know we've seen them before, we've seen them in an earlier algebra class, so this is not brand new to us, but it's important to remember that logarithms are really just exponents. They're kind of like exponents in disguise. Okay, this is an exponential function, really, and since this is just this in a rewritten form, that means this is really an exponential function too. It's just kind of disguised a little bit. It doesn't look like it involves an exponent, but it really does. And so when we do some simple examples to kind of get us going, that's how I'm going to always think of these logarithms, is I'm going to think of them as exponents. And let me do one more thing. Let me just kind of highlight one more thing here on this. Thinking of them as exponents. Notice up here it's b raised to the y. Okay, the y is the exponent. So I kind of think of it like this. This number raised to this power is equal to that number right there. That's kind of how I'm going, that's kind of the logic or thought process that I'm going to follow when I do the problems on the next slide. Alright, so evaluating logarithms. This first one, log base 3 of 27. So for number 1, Okay, this is what I'm thinking. This is what's going through my head. I'm thinking that this means 3, the base 3 raised to what power is equal to 27. Oftentimes this can be mental math. 3 raised to what is 27 is equal to 3. 3 cubed is 27. So again, I always go back to, again, just thinking of logarithms as exponents. 3 raised to this number is equal to this number right here. Okay, so let's continue that thought process then for the rest of these. 2 raised to what power is equal to the square root of 2? Now you might think to yourself that this is the same as log base 2 of 2 raised to the half power. We know that a square root is simply a 1/2 power, and if I see it like that, well then it's quite obvious. 2 raised to what is 2 to the half, and the answer is 1/2. Okay. Next one, log base 4 of 1/16. Well, I know that 4 raised to the second power is 16. To get 1 over 16, it would be 4 raised to the negative second power. Okay. Last two here, log base 5 of 1. So 5 to what power is 1? We know that anything raised to the 0 power is 1. And finally, last one, we have log base 10 of 10. So 10 to what power is 10? That would of course be 1. 10 to the first power is 10. Okay, so there's, again, thinking logarithms. Just remember logarithms as exponents. Okay, and create this kind of circular logic maybe pattern if that helps. Okay, just always thinking 5 to what is 1 and 10 to what power is 10, etc. And you think you'll find logarithms to be not that difficult to evaluate if we think of them like that. Okay, on this slide I want to talk about just some basic properties of logarithms. I'm going to be quite honest with you, I don't really bother memorizing these because I always just refer back to logarithms as exponents, and if I think like that I can come up with these just real quick. But just to be thorough, let me give them to you. I'm going to give you maybe 3 or 4 of them. First one would say, let's just go with log base b of 1 equals 0. And I'm using base b so that that b can be any number that we want it to be. Okay, any base of the logarithm. And the reason why this is true, log base b of 1 is 0, is because any number to the 0 power is equal to 1. So we see log base b of 1, it's always going to be equal to 0. Okay, another basic property would say this. Log base b of b equals 1. Okay, so if you see an instance where these numbers match, right here. Okay, and the reason why, again, is because, I always go back to the power explanation. B to the first power is equal to itself, b. Okay, another property, actually I'm going to give you 2 more. These stem from the fact that exponential and log functions are inverses of each other. So this one here, log base b of b raised to the x is just x. And the last one, let's see, we'll write it like this. B raised to the log base b of x equals x. And again, these are here almost like you say they're inverse properties. Okay, inverse properties meaning that think of inverse operations as operations that undo each other or cancel each other out. If I were to see this log base b of b raised to the x, those cancel each other out. Or if I were to see b raised to the log base b of x, they cancel each other out. they cancel each other out because the b's are matching. Okay, that's very important. We have matching numbers right there. Okay, so let's see some illustration of maybe some of these properties as well. Okay, first one, log base 2 of 8. Now I know the answer is 3, and you're watching, you probably know the answer is 3 also because it is 2 to the third power equals 8. But if I use one of these properties, I could rewrite this as log base 2, 8 is 2 cubed, like that. And then we've got this inverse idea property that, again, if these numbers match, if this number and this number match, and they cancel each other out, and the answer is just 3. Okay. So really kind of two ways to think of that as the exponent or this inverse property idea. Okay, this problem rewritten could be log base 5 of 5 to the 1/3 power. Now again, cube root as a rational exponent. Well, since I've allowed these 5s to match, inverse idea, they cancel out, the answer is 1/3. Okay, the last one, no rewriting is required here of this last one. We've got 5 raised to the log base 5. Again, I'm noticing these numbers matching, so they cancel out, and the answer is just 12. Okay, next I want to go over a couple of special logarithms. First one is a common logarithm. Common logarithm is just a base 10 logarithm. Common because we use it a lot. I guess you could say it like that. So a base 10 logarithm would look like this. Log base 10, right? Well, we change this. The notation for a common logarithm is simply just log. We drop the 10. Okay, so anytime you see a logarithm without a base, okay, so if we see log 100, okay, what it means is log base 10 of 100. So what it means is 10 to what power is 100? 2. Well, this means the exact same thing. You just have to imply and understand that if you don't see a subscript, that it's really a 10. Okay, it's always going to be a 10 if we don't see the subscript underneath the logarithm. So also 2. So that's a common logarithm. A common logarithm is just a base 10 logarithm. And on your calculator, there is a button for common logarithm. Just the log button right there. And you notice above the log button, get a little closer here, is the 10 raised to the x. So they put the log and the 10, the base 10 button, they're inverse buttons of each other. They're inverse functions, but they're second buttons on the calculator. And it should be no surprise that they go together since the exponential and log function are inverses. So they put them on the same button on the calculator. Okay, there's one other logarithm that shows up very often enough that it's worth talking about and defining. Actually, it shows up quite often. It's called the natural logarithm. The natural logarithm is a base e logarithm. Okay, so it is a logarithm of the natural base. And we have kind of talked about what that e is already, so I'm not going to just totally go into defining it. Its notation, as you would suspect, it's a special kind of logarithm, so it gets a special notation. So instead of seeing log base e, what you're going to see is this, just ln. That stands for a logarithm of natural base, and e is the natural base. So you're going to see that. Again, you're not going to see any subscript. You could see natural logarithms written like this, but you'll always see it like this here. And again, it's a button on your calculator as well. So right there to the left of the 4, you see the ln button, and right above it we see the E button, which we've had to use so far a little bit in this chapter. But again, they're on the same button because they're inverse functions of each other. Okay. Now this last slide we'll go over some extra examples. They're going to have this common log and this natural logarithm on this last slide, so we'll just kind of see it in action. Alright, first example, log 100. I know we just did log 100, but just again to reiterate, to reinforce it, this means log base 10 of 100. So 10 to the second power is equal to 100. Now because it's on the calculator, the log button, we can actually type it in. I can actually use this button and type in log 100 and it'll answer for me. Not a problem. This next one, natural log e cubed. Now remember, natural log, and I don't have to rewrite this to show it, I just am so we see it clear. Natural log is log base e, and then I have e cubed, and since those match, they cancel out. Well, they cancel here too. Natural log and e cancel. The answer is just 3. Okay. Now this next one is slightly more challenging, or maybe to do mental math on, but what this means is 10 to what power is equal to 12.3? And I don't know that because 12.3 is not an integral power of 10. So I'm just going to use the calculator to evaluate it. Log 12.3, and I'll round to a decimal. I'm going to use 1.0899. It's generally pretty standard practice to use 4 decimal places when working with logarithms. This last one, natural log of 23.8. Again, what it means is e to what power is 23.8? I don't know that because e is an irrational number. So we're just going to go with natural log 23.8 on the calculator. I'll use 4 decimal places to round that. So it's 3. We'll go with 1697. So in other words, e raised to this power would be 23.8.